Well, thank you very much for the invitation, and I'm honored to be here, and thank you for this nice introduction. So here's a clipping from the Daily Mail, 2010. It says, "Now," this is the Now robot. The Now, the first robot able to feel emotions and to form bonds with humans that look after it. Now, do you believe this? Is this really possible? Now is a very nice robot, but does anybody actually think that it could really feel emotions? I think most people will be doubtful. And in fact, the author of the article here, when you read the article, says, Now has been designed to mimic the emotional skills of a 1-year-old child. And I think this corresponds to the fact that the journalist and most people in the world probably think that robots will never be able to really feel. However, I think most people are wrong. I think there's nothing to stop robots from feeling, and this is going to happen in the very near future. So why do most people think there's a problem? Let's see how we could try to make a robot that really felt something. For example, let's try to see what we would have to build into a robot so it really felt a pain. Okay? In order to do that, let's look at how pains actually occur in humans. So, people know about the anatomy and the physiology of pain. You have a painful stimulus. It excites certain kinds of receptors that are sensitive to painful stimuli. And the information goes up into the spinal cord, and it synapses with fibers which feed immediately back down to muscles that cause your finger to jerk out of the fire. Now that's just an automatic reflex arc. You could easily build that into a robot. No problem. You could get the robot to move its finger out of the fire when it gets too hot. But is that going to make the robot feel pain? Obviously not. Something more is needed. And that's no doubt why in humans and animals, the information is not only connected through this reflex arc, but additionally it goes up to the brain. And so something must be going on in the brain now which makes the pain really hurt, in addition to just having this automatic reflex arc. So let's look at what's going on in the brain. Now, there are many brain areas involved in pain in the brain, and their organization is rather complicated. There are also chemical pathways involving neurotransmitters, serotonin, norepinephrine. But I ask you, whatever the complex circuitry, be it electrical, electrochemical, or just chemical, it's just circuitry, isn't it? How could just circuitry and neural excitation, no matter how complex it is, how could it make you feel the pain? How could just even complex, recurrent neural activation give rise to the feel of pain? There seems to be a fundamental problem here. Let's leave pain aside. Let's talk about perhaps a more basic even question than pain. Color. You look at some colored patches, a red patch and a green patch. It activates areas in the brain that are sensitive to red or green. What is it in those different areas that give you the feel of red or the feel of green? What is different about the brain excitation that gives you the red feeling versus the green feeling? So let's look and see what happens in the brain. You know that in the retina, you have cones that are sensitive to different wavelengths of light. There are 3 kinds of cones, sensitive to 3 bands of light spectra, the long, medium, and short wavelength cones that are sensitive to different bands of wavelengths. And these cones are densely packed in the central retina of the eye. You see they're symbolized here. The three kinds of cones are symbolized by three different colors here. This is how color is measured by the eye. And then higher up in the visual system, it's known also that the information from the three kinds of cones are recombined into three color-sensitive channels. There's a luminance channel that essentially measures the degree of grayness, black and white. And then there are two color channels, one that's sensitive to the equilibrium between red and green, and one that's sensitive to the equilibrium between blue and yellow. So these are physiologically known channels. So the idea would be then that, for example, when you're looking at a red patch of color, that it's sampled by these cones and it's analyzed by the opponent color processing channels here. If the red is a very pure, unique kind of red, you'd expect that the red-green channel would be maximally activated in the red direction. So this channel would be strongly activated, and the blue-yellow channel would not be activated. So a prediction you would make, if you think that the redness of red is generated by the activation in these color channels, and that a pure red then would be caused by the activation of in the red direction of the red-green opponent channel, you would predict that the purest red would occur when this channel is maximally active in the red direction. Unfortunately, that's not true. Measurements have shown that in order for a patch of color to appear pure red, you've got to have some yellow activation. And similarly, in order for something to appear pure blue, you've got to have some green activation. So something is wrong with the idea that color is generated by activation in these color opponent channels. There's something more complex. Well, maybe what's happening, because this is all happening in the low-level visual system already in the retina, but higher up in the brain, maybe you have more complex interactions. So this is a map of the connections in the visual system as it was plotted in 1991 by Fellerman and Van Essen. Nowadays, the connections are even more complicated. So you see that stuff going on in the visual system is very complex. But area V4 is supposed to be particularly involved in color perception. But let me ask you, whatever circuitry there is going on, whatever kind of activity there is going on in V4 or in this whole network, how could any of that activity actually give rise to the red sensation rather than the green sensation? Supposing you found that it was this area here with particular recurrent frequency of oscillation or something that caused the red sensation rather than the green sensation. You could always ask, why? What is it about that particular frequency of oscillation, that particular kind of recurrence that gives red rather than green? There seems to be a fundamental problem here. It seems to be that logically there will be no way of answering the question of why some particular neural process gives rise to this sensation rather than that sensation. And now let me ask you an even more basic question. The question of what we would call sensory presence. Consider that red, for example, gives me a sensory feel. I feel the redness as being present. It imposes itself on me. There is something it's like to feel the redness. But if I just think about red, I don't have that feeling of sensory presence. Why? Presumably when I think about red, there's all sorts of activity going on in my brain. That activity must be different from the activity that gives me the sensation of red. What is the difference? Could it be some special circuitry, some special kind of neurotransmitter, some special chemistry? Supposing it was something in the neurotransmitters, in the visual areas of the brain, that made it that the sensation of red felt like something to me, and that this was lacking in the areas of the brain that involved just thinking about red. Well, then I ask you, what is it about the neurotransmitters in the visual areas of the brain that give me that real feel of sensory presence? And if you say, well, there's those neurotransmitters that are involved in the circuitry that are involved in real sensations of red, they are special because they have, say, an extra nitrogen atom. Then I could say, well, what is it about nitrogen atoms that gives me that feel of sensory presence, which is missing in the neurotransmitters that don't have the nitrogen atom? And then you can make up any story you like. I think there is a logical problem here. Whatever story you make up, if it's a story in terms of physicochemical processes, there's a problem of making the link between that story and the story of what it is like to see red, or the sensory presence of red. There is a logical difficulty here of making the link between what it is like to feel something and neural processes. So this distinction between things that feel like something, things that have sensory presence, and thoughts, memories, and imagining, in order to explain this difference, appealing to neural processes seems to be hopeless. And you could also think of other things going on in your body, autonomic functioning, visceral processes. For example, the measurement of blood glucose is presumably a sensory system in my body, very similar to the sensory system that measures the wavelength of red in my retina. It's a sensory system. Why do I feel the redness, but I don't have any feel of the glucose in my blood? What is it about the systems in the visual cortex that give me the feel, whereas the systems that are to do with measuring glucose don't have a feel? You could argue in terms of some kind of special areas of the brain that are involved which are different, but if there are different areas or different neural mechanisms, I ask you, what is it about those neural mechanisms that is different? And whatever response you give me, I can say, well, what is it about those mechanisms which make it this way rather than that way? I think there's a logical problem. It's a hopeless task, looking in the brain to explain those differences. And this problem has been called the explanatory gap. I've given the examples of making the link between experienced color and known physiology, and of explaining sensory presence in terms of physiology or brain areas. There seems to be no common language between neurophysiological processes and the phenomenal quality of sensations. So now, what can be going on here? What is the problem? Surely what gives us feels cannot be some magical process. Why can we not explain it in terms of neurophysiological processes? To answer this question, let me think back to what happened at the beginning of the 20th century with regard to the question of life. At the beginning of the 20th century, people were thinking about what caused certain systems to be alive rather than not. In order to explain why certain systems seemed to be alive, they postulated a vital spirit, an élan vital, which generated life in biological systems and which was lacking in systems that were not alive. Today we know, and vitalism was an important and scientifically accepted paradigm. Most people were vitalists. But since about the 1930s, there was a change, and modern biology began to think about life in a different way. They realized that life was not the kind of thing that is generated by anything, let alone a vital spirit. Life, they redefined life. Instead of thinking it as something extra that is added into systems, they started thinking about life in another way. They thought that life is a word. It's not a fluid. It's not a thing. Life is simply a word. It's a word that describes the way organic systems interact with their environments. And so they solved the problem of the vital spirit. And that was a revolution in modern biology. And what I'm suggesting is a similar revolution in the notion of consciousness. I think that if we just think about consciousness in a different way, we can create a revolution in thought about consciousness. We should de-reify. We should think about consciousness no longer as being a thing that is generated by the brain. Consciousness is not a thing. It's not a fluid. It's not something that is in brains and caused by brains. Consciousness is like life. It's a word. It's a word that describes a capacity that certain organisms have. It's an ability to do things. And if we think of consciousness as being such a package of possible things to do, in the same way as life was considered to be a package of possible ways of interacting with the world, then we can make a revolution in consciousness research, and we can advance now. So my idea is to think about the redness of red and the hurt of a pain and the sound of a bell and the smell of an onion now, not as things that are generated by brains, but rather as ways of interacting with the environment. Now that doesn't seem to make much sense at first, just as the idea that life was a way of interacting did not make any sense to the vitalists. It requires a leap of faith. It requires adopting a new way of thinking. But to help you adopt this new way of thinking, let me give the example of the sponge, the softness of a sponge. Where is the softness of a sponge generated? Is there a neuron or a neural area that generates the feel of softness somewhere? That seems pretty ridiculous. In the case of the softness of the sponge, we know that the softness is constituted by the fact that when I press on the sponge, it squishes under my pressure. Softness is a way of interacting with soft things. It's not generated. Thinking about softness as being generated by the brain is stupid. It would be ridiculous to go looking in the brain for a softness-generating circuit, because softness lies in what you do when you interact with soft things. It's a mode of interaction. The quality of softness is constituted by, it is a sensorimotor law. It is the fact that when you press, it squishes. And what I want to suggest is that this idea can be applied to all sensations. Red is a way of interacting with the environment. The smell of an onion is a way of interacting with the environment. It is not passively receiving information that is processed by your brain and generating the onion smell somehow in your brain. Now, this may seem difficult to understand. It seems okay for softness, but it's a bet, it's a wager that we have to investigate under the sensorimotor theory of consciousness in order to see whether we can generate useful science by taking this point of view about the feel of sensory experiences. So let's see how we can modify the way we do science by thinking about color in this way. So now, how would you think about color in the new sensorimotor way? Instead of thinking that red is generated by neural activity, we have to think about red as being a sensorimotor law. Now, what could that mean? What could it mean to think about red as a thing we do rather than a thing that is generated by the brain? So with my student, David Philippona, we thought about this for a while, and we had this idea. Maybe red is not the wavelength of light coming into your eye being sensed by red-sensitive detectors. Maybe red is the way red things change the light. So if you take a red piece of paper and you put it under different lights, like under the yellowish sunlight, or the bluish skylight, or the more reddish incandescent light, the light reflected off the red surface changes, of course. And despite the fact that you move the red piece of paper around under different lights, the color of the red surface remains the same to you, even though the light coming to your eye is quite different. This is something that color scientists know. But the man in the street thinks that color is wavelength. But scientists who study color know that that is totally wrong. In fact, if you go into a room which is lit entirely with blue light, and you take a red piece of paper, you bring it into this room, the only light coming into your eye is blue. Because the only light coming off that red piece of paper can be blue, because the red piece of paper can only absorb and reflect blue light. So although the light coming into your eye is blue, you nevertheless see the paper as being red. So the color of red is nothing to do, or little to do, with the wavelength of light coming into your eye. The color of red is a law that describes the way certain surfaces change the spectrum of the incoming light. Now, it turns out that you can do the mathematics of this very easily, because color is measured by the eye using these three cone types, L, M, and S. So the actual complicated spectrum of the yellow light coming into the surface here is measured by these three cone types and can be represented as a point in a three-dimensional space. So incoming light from the sun, for example, corresponds to a point in this LMS space. Some of it gets absorbed and some of it gets reflected by this green surface here. So the spectrum of the light coming out is a little bit different from the light coming in. And the spectrum of the light coming out, when it's measured by the human L, M, and S cones, can be again represented by another point in this three-dimensional space. So what color really is the function that maps this point to this point. And mathematically, this can be represented accurately by a 3x3 matrix. It's a linear mapping. So with my student, David Philippona, we went and looked at different surfaces, and we knew from databases that you can find on the web, for example, what the actual reflectance spectra of each of these surfaces was. And we know what the reflectance, what the illuminant spectrum of the sun and the sky are. And by doing a simple mathematical regression, we're able to calculate for each of these surfaces what the 3x3 matrix is that defines color. So color now is not light coming into your eye. Color is essentially a 3x3 matrix. It's 9 numbers. So we calculated from first physical principles what those 9 numbers were for each of these surfaces. And then my mathematician, Philippona, looked at these matrices, and he said, there's something very interesting about some of these matrices. They are what is called singular. Now, a singular matrix has the property that instead of taking a point in a 3-dimensional space and projecting it into another 3-dimensional space, a singular matrix has the property that it takes a point in the 3-dimensional space and projects it to a lower dimensional subspace of this 3-dimensional space. So in a sense, some of the matrices, the singular matrices, have the property that the light coming out of these surfaces is represented by the retina in a smaller dimensional space than the incoming light. So these singular surfaces have the property of simplifying the light, the spectrum of the light coming in, essentially. And we measured what we called the singularity index of these different surfaces. And here we have the different surfaces, and here is the singularity index for the different surfaces. And you see that there are 4 surfaces here which are singular, that are strongly singular. And curiously, those 4 surfaces that are singular happen to be red, yellow, green, and blue, the so-called primary colors. And that is very interesting. Because if you go to a thing called the World Color Survey, a survey of the names that people give to colors across the world, across non-industrialized cultures. This is a survey where Berlin and Kay, and later Kay and Regier, went throughout the world in the jungle and in the desert, and they showed these colored chips to people and asked them, do you have a name for this? And what they found was that there were 4 chips that everybody had a name for. And these chips were exactly the chips that were singular in our mathematical calculation. Now, this is the first time that a scientific approach from first principles was able to predict an anthropological result here. So I think this is a victory of pure philosophy over science. Because a simple philosophical idea, the idea that we should abandon the idea that color is generated in the brain and instead take the idea that color is a way of interacting with surfaces, this simple idea, plus some mathematical calculations from first principles with no parameter adjusting, has given rise to an extremely accurate prediction that no one else has been able to confirm, that no one else has been able to predict. And these peaks in the singularity plot and the World Color Survey are the same. And let me go back to the question that I mentioned at the beginning, where it turns out that in order to see a surface as uniquely red, you have to add some yellow, something that nobody has understood up to now. Again, the theory is able to perfectly predict those results. Another way I won't go into the details, another way of showing these results about unique colors, unique red, unique blue, etc., is to show these plots here of the data of people adjusting colors to appear unique. And if the simple idea that the color opponent channels were generating unique colors were true, then these data points should lie on a vertical and horizontal axes. But you see they're not off. They're not on them. And for example, in order to see unique blue, you need to add in a little bit of green. To see unique red, you have to add in a little bit of yellow. But you see the black lines here? They're the predictions from the sensorimotor theory. They exactly predict the observed results. Another victory of philosophy over science. So I've shown you how a simple philosophical idea about what feel is, what sensations are, has made a scientific prediction which is surprisingly confirmed about unique colors. I would like to have had time to go through some other predictions of this philosophical idea. I'm going to talk about sensory presence now. I won't have time to go into the others. So let's look at the other deep question that I mentioned at the beginning of the talk, sensory presence. I told you that there seemed to be no logical way of explaining why it is that red feels like something, but thinking of red feels like nothing. Red feels like something, but blood glucose level in my body feels like nothing. Why? And you can't explain this from appealing to neural networks or anything in the brain. What does the sensorimotor theory have to do in order to provide an explanation of this? It has to look to see, well, what it is about interacting with the world in a way that corresponds to the laws of red or the laws of onion flavor or whatever. What it is about interacting with the world in this way that differs, that gives these interactions a feel of something it's like, as compared with interacting with the world when you're thinking of red or when blood glucose level is being measured. So I need an explanation in terms of these sensorimotor laws. So let's look at what kind of sensorimotor laws are obeyed when you are looking at red or hearing a noise. What are the sensorimotor laws? Well, obviously, well, I've isolated 3 aspects of real-world interactions which I think explain or correspond to this notion of sensory presence. And these 3 ideas are what I call, these 3 types of laws are what I call bodyliness, insubordinateness, and grabbiness. So if you are really looking at a red surface, and you move your head and you move your eyes, well then on your retina there will be enormous changes. You move your eye on and off the red surface, there's an enormous change on your retina. The sensory input changes drastically. But if I'm thinking about a red surface and I move my eyes, nothing happens. So that's what I call bodyliness. If you are interacting with the world using your senses, obviously moving your body is going to dramatically change the sensory input. But if you're thinking about it, it won't change the sensory input. That's what I call bodyliness. So bodyliness is one measure of the fact that you really are interacting perceptually with the external world. What about blood glucose? If your sensory systems are measuring blood glucose, you move your eyes, you move your head, it doesn't affect blood glucose. Visceral properties, visceral measurements have no bodyliness, or very little. Obviously, if you run very fast, it will deplete the glucose level. But the effect of moving your body on blood glucose is much less than the effect of moving your eyes on seeing red. I think what characterizes all sensory systems is the fact that moving your body drastically affects sensory input. So that's bodyliness. Insubordinateness is the fact that although there is this systematic bodyliness, it is not complete. So sensory input can also change without voluntary actions. So even though it's true that if I move my eyes, it drastically changes sensory input when I'm looking at red, it's also true that if I'm not moving my eyes, there can be a sudden red flash. So that is insubordinateness. It means that the outside world imposes itself on us. We do not have complete control of the sensory input that we get from the outside world. We are partially under control of the outside world. Our sensations are partially insubordinate to the outside world. The outside world exerts some control on our sensory systems. And then there's grabbiness. Grabbiness is the fact that sensory channels seem to be hardwired so as to cause our attentional and cognitive faculties to be oriented to sudden changes. If I make a big noise, you cannot but orient your attention to this noise. If there's a sudden flash of light, you have automatic orienting reactions to it. Now, these, so bodiness I've talked about, insubordinateness, grabbiness, the capacity to peremptorily interfere with cognitive processing. I think sensory systems are hardwired, anatomically hardwired, to interfere with processing when there are sudden changes. Hardwired transient detectors in vision, audition, touch, smell, taste. Take the vestibular system, for example, or proprioceptive systems. You could ask, why is it that we don't feel the vestibular input? Why is it that that proprioception is not generally considered to be a sense modality like hearing or seeing or smelling or touching or tasting? And I claim it's because these modalities do not possess all of the 3 requirements for something to have something it's like: bodiness, grabbiness, and insubordinateness. So in particular, proprioceptive input doesn't have grabbiness, I suggest. But this could be debated. I think, in general, thoughts and imaginings also don't have grabbiness. You are in charge of your thoughts. You cannot surprise yourself with your own thoughts. Changing your thoughts is under your control. So thoughts don't have grabbiness. So let's see how these ideas work with regard to seeing. When I'm seeing something rather than just imagining something or thinking about it, I have the feeling that everything I see in front of me imposes itself on me and there is something it's like. Whereas, as I said, glucose level or imaginings don't have anything it's like. Why is that? In the sensorimotor theory, I have to appeal to certain sensorimotor laws, and in particular, the bodilessness, grabbiness, and insubordinateness of the visual modality, which I claim accounts for the degree of sensory presence of vision. So clearly, vision has bodiliness because it depends on body movements, unlike thoughts, imaginings, and autonomous processes. Movements of my body drastically change sensory input. I already said that for vision. Insubordinateness, I can be looking around and a mouse can flit across the floor and that changes abruptly the sensory input and it's not under my control. Right? My senses are insubordinate to the outside visual world. And then there's grabbiness. No doubt you've seen these change blindness demonstrations. Clearly, if something happens in the visual world suddenly like this, because of the grabbiness of the visual channels, this abrupt change in the visual field causes your attention to go to the change and you immediately see it. So this shows the grabbiness of visual channels. But the hypothesis would be that if through some artificial trick I was able to prevent the grabbiness detectors in your visual system from orienting my attention, then I should be able to make big changes in these pictures without you seeing it. Because my claim is the impression of seeing derives from, or partially from, the grabbiness of the visual field. If I remove that grabbiness, I will no longer have the impression of seeing. And that is why this theory predicts change blindness. If I should make a change in the visual field, but this change occurs so slowly that the grabbiness detectors in the visual system are not activated, well then you can be looking at this picture and still not see that there is an enormous change that has occurred here. This is a different picture from the one that you saw a minute ago. I don't know if you've seen the change here. This is a completely different picture from the one that came up. However, the change has occurred so slowly that it did not attract your attention to it. And so you, even though you think you're seeing everything in the picture, you actually don't see this big thing that has changed. However, if I make the change suddenly, then it will immediately appear to you because the grabbiness of the visual system will attract your attention to it. So here is the sudden change. The whole of the lower area here was red to begin with, and I changed it to blue so gradually that you did not see it. So this, of course, is a big literature, and what I stress is that this literature was generated by the prediction of the sensorimotor theory. So it's an example of another victory of philosophy over science, because a simple philosophical idea about what we mean by sensation predicts this change blindness phenomenon. It's a big literature. However, I must admit that my own colleagues who worked with me on this now do not believe my theory. They have a representationalist theory about it, which is of course possible. Once you have found a result, there are of course many different theories that will be compatible with that result. But what I wish to stress is that it was my version of the theory which predicted the result and generated the scientific paradigm. So to summarize here, this change blindness stuff illustrates how, along with bodilessness, insubordinateness, and grabbiness is an important factor in determining visual presence or visual what it is like. When we artificially remove the grabbiness of the visual field, well, then you simply do not see things anymore. Now, exactly the same idea, these notions of bodilessness, grabbiness, and insubordinateness, I think, could now be applied to other sensory modalities, and you could make what I call a phenomenality plot, where you plot the amount of bodilessness, grabbiness, and insubordinateness on a third axis of different mental states, mental phenomena, and you should make the prediction that the more grabbiness, bodilessness, and insubordinateness you have, the more you have what you could call sensory phenomenality. The more something should appear to have something it's like. But this would be a future scientific project to investigate how, for example, hunger, thirst, fear, anger, love, embarrassment, feelings of hotness, calmness, wetness, all these feelings could be positioned on this phenomenality plot, and how we would have to predict the degree to which people would agree that they have more or less sensory what it is likeness or phenomenality. So I've described how the sensorimotor approach makes predictions about color, about sensory presence. I don't have time to go into some other applications here. Just to summarize, the advantage of this approach is it bridges the explanatory gap. It solves what's been called the hard problem of consciousness, of what feels are like, why there is such a thing as sensory presence, and it generates scientific research paradigms. And the underlying idea was that instead of taking the standard view according to which the brain creates feel, generates feel, like a vital spirit generates life, we take the alternative sensorimotor view, which is that feel is a way of interacting with the environment. And in this idea, in this sensorimotor approach, the quality, the experience quality of a feel is constituted by the sensorimotor law that is involved when you're experiencing that feel. And this explains how different feels differ, like why red is different from green, why colors, why vision is different from audition, etc. And it explains sensory presence, why vision, for example, feels like something, but glucose level feels like nothing. However, this is just the quality of the feel. And it seems to me that the sensorimotor law that describes how sensory input changes when you act, such sensorimotor laws could be possessed by machines. I could take a thermostat or a bulldozer or a robotic gripper. The robotic gripper could grip the sponge, and it could press on the sponge, and the sensory input coming back from the sensors on the gripper could be compared to the motor output of the motor commands on the gripper, and there would be a sensorimotor law there. But nobody would say that the gripper felt anything. So something more is needed. What is needed is a higher form of cognition. You have to have cognitive capacities that allow you to attend to the fact that you are gripping the sponge. If I am sensing the sponge right now, and I'm talking to you excitedly about something, I could be sensing the sponge with my fingers, but I would not be consciously experiencing the feel of softness. Consciously experiencing the feel of softness requires me to be mentally accessing the fact that I am engaged in this sensorimotor interaction. And what I mean by cognitively accessing is I have to be poised to make use of the fact that I'm interacting with the sponge in my behavior, in my linguistic acts, in my planning. That's what I mean by attending to and making use of the fact that I am engaged in this. So what we mean when we say that we are consciously experiencing something is that not only are we engaged in interaction with the environment that obeys some sensorimotor laws, but in addition, we are attending to that fact and we are poised to make use of that fact in our rational behavior. Now, attention, of course, is something that psychologists have studied for years. This is an attention test for you. You have to follow the coin underneath the cup. And it's a little bit difficult because there's lots of other cups moving around. Now, where is it? There. Okay. Now, who saw the green pepper? I think maybe some of you have seen this demonstration before, because, well, I think at least half of the people here did not see the green pepper. I will show you the demonstration again. There's a green pepper that moves across the visual field, right in the middle of it, and yet you don't see it if you're concentrating on where the coin is. There. Now, of course, I had to make that demonstration because you all know the famous Simons and Chabris gorilla experiment, where a gorilla moves across the scene and nobody sees it. And this phenomenon that everybody knows is called inattentional blindness, and it's a visual analog of the auditory so-called cocktail party problem. When you're paying attention to one thing, you don't see another thing, even though it's right in the middle of your visual field. And this is actually at the root of a lot of traffic accidents. In fact, it's the third most common cause of traffic accident after drunken driving and driving in the dark in bad visual conditions. And what happens is you're driving along the road and you're coming up to an intersection and you look into the intersection and a motorcyclist is coming in from the right, and you look at the motorcyclist, but you don't see him. And you crash into him, and he is very badly injured. And so weeks later, you go and visit this motorcyclist at the hospital, and you come up to the motorcyclist and you say, "I'm terribly sorry, but I didn't see you." And the motorcyclist says to you, "But I was looking at you and I saw that you were looking straight at me." And that's the phenomenon of looked but failed to see. And it's a well-known phenomenon in traffic security. As I said, it's the third most common cause of accidents. And it is the fact that seeing is not looking. You can look at something, but that does not mean you see it. And that is because seeing is not having something in your retina, on your retina. Seeing is not having excitation of neural activity in area V1. Seeing is interacting with the visual world in an active way. It's making use of of the information you're getting. It's manipulating it in the same way as touching a sponge is manipulating the sponge. Seeing is manipulating the visual world. And so you're only really conscious of seeing something when you are paying attention to the particular thing that you're interested in manipulating. So, for example, when I look at this room here, my claim is, actually, I have the impression of seeing the whole room here in infinite visual detail, and it's all completely present to me. But actually, I claim, this is an illusion. I do not see the whole world really in detail. I am actually only at any moment extracting one particular thing that I am visually manipulating at a given moment. I extract the particular detail that I'm asking myself about at this moment, plus, of course, I have some notion of the global fact that I'm looking in a room full of people. So the reason why the world appears to me to be completely present and so wonderfully rich and colorful to me right now is not because I have some internal representation of the outside world which is active and completely detailed. No, I don't have to have an internal representation because the world is out there like an external memory. And if I want to know whether the door or the window is there, I just move my eyes there, and yes, I can check it's there. So the fact that I have the feeling of seeing everything now derives from the immediate availability of anything that I might just be interested in through a movement of my attention or of my eye. So really, seeing is an illusion. Now, an example is here. Many people read this and they say, it says the illusion of seeing. Raise your hand if you see something different from the illusion of seeing. There's actually a mistake here. It does not say the illusion of seeing. It says the illusion of seeing. You do not see what is out there. Seeing is manipulating, and it's strongly determined by prior knowledge and expectations. And the continuity, the apparent fact that the visual world outside seems continuous to me and not interrupted by my eye movements and blinks. The fact that everything is continually visible all the time, despite the fact that I am only sampling things with my attention in a discontinuous fashion, that illusion also is generated by the fact that things are immediately available whenever I look. It's like the light in the refrigerator. When I open the refrigerator, the light is on. I close the refrigerator door, and I wonder, is the light still on? Sneak it open, it's still on. Whenever I open the door, however quickly I do it, the light is always on. So it seems to me that the light is always on. And it's the same about the visual world. It seems to me that it's always there. But the continual presence of the world outside does not require that in my brain the world has to be continually represented. In fact, to think that in order to see the world as continuous in time, I need to have a representation in my mind which is also continuous in time, is to make an egregious philosophical error. It's the same error as to think that in order to see redness, I would have to have a red fluid oozing out of my nerve cells. It's what the philosophers call the content-vehicle confusion. Seeing something as continuous does not require that the representation or the neural activity that corresponds to that notion of continuity itself be continuous. Because the neural activity is just a code, and anything can code for anything. The code doesn't have to be continuous in time or in space in order to give us the impression of continuity. So, in conclusion, up to now, consciously experiencing a feel has two components. It involves interacting with the world according to sensorimotor laws, and the quality of my experience is constituted by the sensorimotor laws that describe that experience, objective sensorimotor laws. And this explains why feels feel the way they do and why they have sensory presence. But there's more, because mere machines could have this. There's more, and it requires cognitive capacities, attention, cognitively accessing. But there's another problem. Who is cognitively accessing? I just used the word I, but who is I? How can we explain the cognitive self? Now, I think I'm not going to go into details on this. I think I'll stop here. But I think I have a way of conceiving the notion of the self essentially as, well, there's a cognitive self, and I'd say there's a social self. The cognitive self involves three levels of cognitive, a hierarchy of three levels of information. A system can distinguish itself from the outside world, but even bacteria, for example, don't eat themselves up, so they must distinguish between them and the outside world, so it's something very basic. At a higher level, you have self-knowledge, perhaps higher level nervous systems are able to know that they do not eat themselves up, and they can even have some form of goal and planning. For example, a bird will hide its nuts or worms from other birds, or squirrels will hide their nuts from other squirrels, showing that the squirrel essentially knows that it is different from other squirrels. It has goals, and it plans. It has a primitive form of reasoning, but it doesn't itself know that it does that. That involves knowledge of self-knowledge. So this knowledge of self-knowledge would be a higher form of cognition. But there's nothing magical about this, okay? This higher level of self-knowledge involves something like a theory of mind, empathy, beliefs. It could even give rise to more complex behaviors like selfishness, cooperation, and give rise to things like shame, pride. It gives rise to what the philosopher Dennett calls the attentional stance. These are higher level cognitive activities, which I think constitute what we could call the cognitive self. But I don't think there's any magic about that. And so I think that it's accessible to science. But still you might ask, why do we, if this is just some computational mechanism that goes on in our head, why do we have this strong sense of being a person, of I? Who is I? Okay? Now, my theory about this, and I think a lot of social psychologists will agree with me, is that the notion of I is actually a cognitive social construct. Okay? It's a useful abstraction for describing ourselves. It's what Dennett called a narrative fiction. But why does this I, if it's just a story that we're telling ourselves, why does it appeal so real to us? Why does it appear so real to us? I think it's real to us because it is real. It is an important aspect of our social interactions. Just like money, which is just bits of paper, for example, is perfectly real nevertheless. It has value despite the fact that it's just bits of metal and bits of paper. But in fact, the social self, the I am even more real than money because it's self-referring. Money doesn't refer to itself, whereas my I refers to myself. So it's an interesting kind of loop there. Hofstadter has talked about this bizarre loop that this involves. And you could also ask, how is it possible that this I actually has the property of having the notion of agency? How is it that such a fiction, a story, how could a story cause me to move my hand? And I think the biologist Terence Deacon and also Mark Bickard, they have ideas about how such a complex hierarchical system could give rise to the notion of agency. But it's interesting because if I am just a story that I am telling myself, you could ask, well, if it's just a story, why don't I just change it? I should be able to easily change myself. And I think you could ask, well, why is it that it's so difficult to change one's personality? I think it's part of the story of I that it is a taboo of changing. I think we are all indoctrinated to think that we actually cannot change ourselves. However, if that is true, supposing that theory is right, well then knowing that it is a taboo, it should be possible to actually break the taboo. And I think the fact is that society does provide us with ways of breaking the taboo. And there are voluntary ways and involuntary ways of breaking this taboo. Voluntary ways are what are called culturally bound syndromes. So in many societies around the world, there are ways in which people can change their personality in a kind of voluntary way. And for example, there are things called possession trances, ecstasies, channeling, oracles, lata, amok, korozar. And hypnosis is a culturally bound syndrome that we here in our Western culture use to change our personalities. Hypnosis itself is a culturally bound syndrome. Apparently, you cannot hypnotize somebody who has not heard about hypnosis. You cannot go to a native culture in Africa or in I don't know where, have never heard about hypnosis and say, I'm going to hypnotize you, and people will get hypnotized. Because hypnosis requires the hypnotized person to know what he is supposed to do. Essentially, hypnosis is playing a game that is socially accepted. And you could ask, well, why is it that that if it's just playing a game, it seems so real and we are so convinced of this? But I tell you, a thing like a notion like love, for example, essentially romantic love as it is known today, is just a socially bound syndrome. In the Middle Ages, in the early, before the Renaissance, the notion of romantic love didn't exist. I am told. I'm not an expert on this. I think, and nevertheless, people kill for love. They commit suicide. Horrible things happen for love. You really feel these things, even though they are just stories. Like money, these socially bound syndromes are perfectly real, and we feel them. So myself, I am just a story, and yet it feels very real to me. And of course, you can change the story also involuntarily through abuse, brainwashing, dissociative identity disorder, etc. So I think that under these views, the notion of I is also accessible to science. So, I can come to the conclusion. I think I've given you an account of what it why things feel the way they do. You need a low level and a higher level approach to it. It's a kind of embedded system. The feel of an experience is like a skill, the exercise of a skill. Thinking and remembering, for example, are skills, but they don't have bodiliness, grabbiness, and insubordinateness, so they're not sensory experiences. The quality of a sensory experience is determined by the different laws involved in the sensorimotor interaction, and you need a higher order cognitive access in order to be conscious of a sensation. So I hope I've convinced you that now the robot could actually one day, in the near future, really have feels and have cognitive access in self. Emotions I haven't talked about. I think emotions are like feels, but you have added into them actual physical reactions on the part of the body. So I think, yes, in the next 20 years, we're going to have robots that really have feel. Thank you very much.